Hello, welcome back to the introduction to biomaterial. And this is the part 2, MXC 2.04. I hope you enjoyed the movie that I will recommend after previous introduction to biomaterial part 1. If you haven't finished watching this introduction to biomaterial part 1, click on the link given in the comment sections. Then you can finish fast and then you can continue to the part 2 of the introduction to biomaterial. So let's briefly talk about what we have been so far talking in the part 1 of the introduction to biomaterial. So we've been so far talking about the two disciplines that we need to have in background, so which is the engineering and medicine. In more detail, which is about the material science and also the biological science. And the basic understanding about these material science and biological science, and also the integration between these material science and biological science. So that is what we've been so far for each session. But here in this part 2 of the introduction to biomaterial, I will more into detail about the integration, what is going to happen between the material and biological environments. So the material that we're going to implant into our human body, and also how the biological environment will respond to the biomaterial. This is the figure that the biomaterial will be implanted into the human body. So at the bottom of the figure, which is in the gray color that we can see clearly, is the implant biomaterial. So this is the surface of the implant biomaterial. Okay, after a few seconds, these implants biomaterial was going to be inside the human body. The first a few seconds, what is going to happen is that there will be protein absorption. So the protein will be absorbed on the surface of the implant biomaterial and followed by, as I already mentioned before, the defense cell, our immune cell, was going to come to the surface together with the proteins, so such as the neutrophil. And the neutrophil will come first to the surface of the implant biomaterial. After that, on the second stage, which is after a few minutes later, there will be matrix deposition. In this case, there are more immune cells, such as monocyte, will come, macrophage will come together. After that, there were some kind of cells, such as fibroblasts, in the state of the fibroblast encapsulation. And also, they have so many different kind of cell will come together and then do the encapsulation of this bio implants material. This is what's going to happen within 1 or 2 hours when we start to implant the biomaterial into our biological system, our body. So in this case, how we is going to design the biomaterial that we are going to implant in our body. So in this case, they have two different types of the biomaterial, so which is the bio-inner biomaterial and bioactive biomaterial. So you see very clearly even in the names, right? Bio-inner material is like a bio-invisible, but invisible to the biological environment. So this material is designed to be invisible to the biological environments, but it should be biocompatible. But invisible means it don't injure any biological interactions between the bioimplant material and biological environment. That is, we call it bioinert material. So bioactive material, on the other hand, which is very active material, not added to the toxicated, not added to, not being good for the bioimplant material, but it's good for compatible, that's will support for the cell function like adhesion, separation, migrations, growth, such as something like that. So these kind of biomaterial, we call it bioactive material. So we know bioinner and bioactive are two different kind of the biomaterial. So let's make more clearly. So bioinner material, as I mentioned before, they on the surface of the biomaterial, so there will be no absorption of any other biological molecule or cell. So like proteins or the immune cell or whatever the cell in the biological system is, there will be no attachment. They will stay, this biomaterial will stay alone. They will stand together. But for the bioactive material, the surface of the biomaterial is modified internal to be able to integrate with the biological system, and in a way of to be able to absorb on the surface of the biomaterial by the other biological substances such as the proteins, biological cell, something like that. So this is what the difference between bioinert material and bioactive material. So the main important things of the biological material is that biocompatible, as I mentioned before. Biocompatible is very important property characteristics for the biomaterial to be able to integrate into the biological system. Okay, with the host tissue that should not be provoke any rejection, inflammation, or immune response to the biological system. So this is how the biomaterial should be able to have the property like a biocompatible. And also there are a few characteristics, but it's also important, but it's also depend on the function of this biomaterial that we are going to implant into our human body. So for example, vascular supported. So that is the how this biomaterial should be able to support to the flow of the blood in a way that the blood vessel should be able to allow to integrate with the biomaterial to be able to flow the blood into the host our organs. So this is one characteristic, but it also depends on the function of the biomaterial. And also this one, non-toxic, it is very important for all biomaterial. So because it should not be produced any toxic substance in our biological system. And another one is non-immunogenic. That means it should not be immune any immune systems to make this attached to the biomaterial itself. And also important thing is non-corrosive. If this biomaterial is corrosive to the human's biological system, so that is very dangerous. Because these are the corrosion is releasing ion into our human biological system that is not just destroying the cell but also destroying our DNA structure. That can lead into the chain of the genetics and the cancer potential disease, something like that. And also if the biomaterial have a high surface area, that has very good a point to be able to modify the surface, make it more biocompatible, and also make it more compatible with the biological cell and tissue. And another thing is mechanical strength. This is quite much dependent on strength. What is the function of the biomaterial that we are going to use? Any place of the replacement of the bone, or any place of the functioning or the diagnosing our human body or something like that. That is depend on the function of the biomaterial that we are going to use. The last one is sterile silver. That means that after preparation of the biomaterial, so these biomaterial should be sterilized, make it more to be able to compatible with the biological environment, not to be giving the toxins, not to be any other material or such as a harmful substance to our humans biological system. So here I want to emphasize that the more important thing is the biomaterial should be biocompatible. So how biocompatible it is that? So between the biomaterial and the host, they should able to stay together in a way that these materials supposed to the biological system, and also these biological system could be able to adaptable with the biomaterial to be able to function our humans biological system. That is how important of the biocompatibility. So here I want to give you the one example. That's how the biomaterial in the bone regeneration report the evolution of these biomaterial. So in the early centuries, in 1960, the biomaterial has already been used for the bones biomaterial like a bone replacements or bone supporting material. So in that case, we're using the metal alloy, just like a stainless steel titanium alloy that has been used for such a long time, since 50 years ago, 60 years ago. And then this is the first generation. After that, in the late 19th century, they have a new biomaterial, which is the bioceramics and biopolymer. That's the new generation of the biomaterial. In this generation of the biomaterial, these biomaterials could be able to like a bioactive material. So the first generation is bio-inert material. After that, the second generation is became the bioactive material and also bioresorbable material. In this case, we use the bioceramics and biopolymer. And the current ones, we are using the third generation, which is bioactive, bioresorbable biomaterial. But the same a functional biomaterial. But the other thing that is making more to be able to more efficient is that they are in the scale of the nano scale, and also they are compositing with other different material. So that's the efficiency of the bioactive and bioresorbable is make more efficient. And the last generations, which is the fourth generation, which is 2020, that is what we are trying to achieve, this kind of tissue engineering scaffold. That is bio-mimetic biomaterial. Here, I will give you one example about how bio-mimetic biomaterial have a high potential to be able to integrate for the bone regeneration and repair. So first, let's take a look about the structure of bone. So if we are going to design the fourth generation of the biomaterial for the bone regeneration and repair, that we need to understand about what is the structure of the bones. So this is the long bone, the femur. So in the long bone femur, when we cross section, these are the femur, the long bone. The inside, what we see at the middle, so we will see that is the bone marrow. So the bone marrow, we have the yellow bone marrow, and also we have the red bone marrow. So the yellow bone marrow is at the center between the inside of the femur. So at the edge, we will see the red color, which is the red bone marrow. So in that case, when we closely take a look on that's the edge of the long bone. So in the area of the red marrow area, so the outer surface of the bone is the compact region, but the inner core of the long bone is with the spongy area. This spongy area have a very small hole. So this small hole is very important. This small hole have many different functions. That is taking place in this place. So this kind of bone, as I already mentioned before in the first part of this introduction to my biomaterial, I mentioned about the bone generates blood cell, so such as the white blood cell, red blood cell, the platelet, something like that. The blood cell are produced in this long bone. So this spongy is a plate that these cells could be able to differentiate by the stem cell, or it could be able to proliferate into a large number of the cell to be able to produce a red blood cell, white blood cell, something like that. And also the spongy size, small pore is be able to transport the nutrition to be able to survive for these kind of cell, to be able to differentiate, to be able to proliferate. So that's itself the function of the bone. And also there is the process, which is the osteolysis, this kind of process, how these bones could be able to regenerate itself by means of the functioning of the cells, like osteolysis, something like that. So this is how the spongy area is very important as a place like a home for the red blood cell, and also be able to support the nutrition to these kind of cells to be able to differentiation and proliferation of the cell. So this is very important. So here we are going to engineering about this for the bone regeneration. In this case, we are going to mimic this spongy area are the real bones, and then we're going to fabricate just like the spongy material. So we call it scaffold. So to fabricate this kind of spongy, the very small hole, like we call it scaffold, we need to think about what kind of material we're going to use it. We're going to use just only ceramics, we're going to use just only polymer or metallic material, or maybe we could able to use all these three things together and design for this scaffold, because it is not just important for supporting the physical strength of the function of the bone, but also it's important to be able to survive the cell and also to be able to proliferate in this place, just like a home for the cell to be able to proliferate in this place. So we designed using different type of the material and together with, and then we designed to have the spongy scaffold biomaterial, which I've shown in here. After we prepare this material, so these materials should be bound compatible. It's very important thing. After we prepare this scaffold, the next thing is that we're going to make it to let the cell growth in this scaffold. So in that case, so we is going to put the cell, that's a bones generated cell, osteoblasts, this kind of cell is going to put into this scaffold to be able to proliferate. And then we're going to put together growth factor and other bound active molecule that will support these cell to be able to proliferate in this scaffold. And also we could able to add another catalyst just like a chemical compound, ions, or function nanoparticle that will able to accelerate the proliferation process, and also be the improvement of the biological system for being able to these cells to be able to proliferation. So after consideration of so many different factors, and the last one is that to make these kind of cells to be able to proliferate in this scaffold, we need the biological system, right? So to make this the same biological system, we need to create a bioreactor. So in this bioreactor, so we're going to put the scaffold together with the cell and other growth factor in the bioreactor system. Let them proliferate these cells in the scaffold. After that, now this proliferation of these cells have enough number of the cells that have already proliferated in this scaffold. And then we will replace, and also we will put onto the broken part of the bone that is going to help to support and internal mechanically, and also internal the to be able to functions of this bone, such as like generating the bone marrow cell, generating the blood vessel cell. So this is how the last generation of the biomaterial for bone regeneration report. Okay, that is how after growing, so we can use this kind of scaffold grow together with the cell, and that can replace to the broken part of the human body. So the next one is that it's not just for the bone, but also the other part of our human body can be replaced by these kind of scaffold. So this engineering, the research group, they prepare using the polymerase material by using the 3D bound printing process. They design the scaffold. First, they design this scaffold to be replace the ear of the human body. And then they make big improves in the figure B as shown in, make it more in strength of these 3D printed scaffold by lining us with the strong polymerase material. After they have designed, they certify with this, okay, scaffold by 3D printing process. And then they grow it in the bioreactor process and using the stem cell taken from this human body that we are going to implant it. So next, this lady has got the implantations. This is what happens. Got the implantation that's grow this ear out in the lab, and then now he or she could be able to have the ear that's already grown in the lab. This is how biomaterial is important it is. This is another class of biomaterial. So the previously I talked about the bone biomaterial, especially the big size of the biomaterial. Here is the small size of nanoparticle, the bound nanoparticle, which have the polymerase bound nanoparticle, ionogenes, or lipids. They are different function. And they have the good point, they have the weak points for each type of the nanoparticle. For example, polymerase nanoparticle, these polymerase nanoparticle can be able to control the size very easily, precisely. But the thing is that they could able to occur aggregation and toxicity. But that is how we're going to figure it out to overcome, not to ever do aggregation, not to be toxicity. So this is the polymerase. So in ionogenes particle, this is very important nanoparticle because these kind of nanoparticle could be able to use not just for the delivery of the drug in our body, but also just like the direct treatment by using the nanoparticle, and also technoxid, and also the sensor, biosensor nanoparticle. So they have many different functions. And also the last one is a lipid-based nanoparticle. So these lipid nanoparticles are very easy to do the synthesis to prepare the lipid nanoparticle. But the other terms, they have the low encapsulation efficiency. And this is the way that's how we could able to improve to get the high encapsulation efficiency of lipid nanoparticle. Okay, let me think about how we are going to engineer these nanoparticles for biomedical application. So the first things that we need to think about is that what is the size and shape of the nanoparticle? This is very important. So to us going to function the nanoparticle in our body. So which place we are going to go by using the nanoparticle? In that case, we need to think about what is the size that we need to use, what is the shapes we need to use it. So this is the first thing we need to think about it. After that, we need to think about it, the surface charge of this nanoparticle. Okay, the surface charge is not just important for the stability of the nanoparticle, but also could be able to use to do the surface coating process. If surface charge of the nanoparticle is negative, we can use surface coating by using the positive polymerase material. So this is how we could able to design the surface of the nanoparticle by using the positive and negative charge interaction to be able to compatible with the biological environments. After preparation of the surface of the bio nanoparticle, that could be able to compatible with the biological environments, we need to think about targeting. Okay, these nanoparticles we're going to target it in which cell. So in that case, targeting could be by using carbohydrate or maybe antibody antigen interaction or bind or receptor or bind of peptides. This is how we could able to target by using the different biological substance that could able to reach to the specific place of the in our human body. That is how we can engineering the nanoparticle for the biomedical application. So this is one example that's designing this nanoparticle for the cancer detection and therapy. So here we're using the PFB. This is the liquid PFB. This liquid PFB is encapsulated by the matrix of the polymer and also SPI1 and DIR. by in preparation with the ultrasonication application, processing, ultrasonic processing. So after that, the PSP liquid is encapsulated by the polymer and the ice-beam of the matrix. So the surface of these nanoparticle will be conjugated with the half substance. Thus will be targeted to the HER2. So HER2 is the breast cancer cell. So the things that with the designing the nanoparticle is that to kill the breast cancer cell, which is a HER2 breast cancer cell in our human body. So to go to the target to the HER2 breast cancer cell, so the surface of this nanoparticle is conjugated with the half substance that's target to the HER2 breast cancer cell by using the EDH and NHS chemistry, which is the covalent bonding between the half substance and the functional group of the polymerase surface material. So after that, after we designing these nanoparticles, these nanoparticles are injected to our human body. After a few hours, the nanoparticle will reach to the HER2 breast cancer cell and then will go inside into the breast cancer cell. After that, we're going to illuminate near-infrared laser that will activate the giving the heat enough to do the preparation of the PSP liquid and also producing the bubble. These are giving the high pressure in the cell that will destroy these breast cancer cell. This is the one thing. Another, and then SPIO and DIR will also be released from this method of the PEG and PLGA polymer matrix, and they will be used by for the prototype therapy by the outside in the additions using the MRIs or NIRS, these kind of additions, and then they will give the photo to the thermal energy and then the world case to the cancer cell. This is another one how we could able to design the nanoparticle for the cancer detection and also the cancer therapy. Not just for the therapy, but also we can use the biomaterial for the sensoring, monitoring our biological system, biological condition. So here, this research group, they use a graphene tattoo. So the graphene tattoo got a signal of the blood flow and then give the electrical signal and then it generates to the blood pressure. So this is how the graphene material should be able to bound compatible to be able to use the graphene tattoo that's able to monitor of the blood pressure. So this is the latest one, very important biosensor. That is monitoring how the biochemistry is happening inside our body. So this is already in the market, in the market. So under the skin cell, the small round biosensor is placed under the skin cell. So this sensor is very small, 5mm long, and the diameter is about 2 to 4mm. The below the skin is a 2 to 4mm. So these are long range biomaterial can be able to detect the biological systems that what is happening inside in our body, and also these biomaterial can emit the signal to the outside, and we could able to monitor what is the level of glucose, what is the level of oxygen in our body. So that is very important thing. So in this, the future research of the biomaterial is not just the treatments, not just treatment of the disease, but also continuous monitoring of the biological system. In this case, these biomaterials should be able to not just compatible with the biological system, to function the biological system, not to be a toxic the biological system, but also they can sense the biochemistry process, what is that's happening inside our body. And one more important thing is that they can emit the signal that's let us know about what is biochemistry is happening inside our body. Then we could able to know what is happening inside our body, and then we can know how we can able to adapt to be able to healthy our biological system, our human body. So that is how biomaterial will plays a very important role in a place of the continuous monitoring or the biosensing, and also giving a signal and giving a large amount of data what is happening inside that's could able to give our healthy light. So here is the few reference that I would like to provide you all. If you are interested in the biomaterial, you can able to download these reference over the internet. And I hope you enjoy this part 2 of the introduction to biomaterial. Bye-bye.